Hello students, this is probably the last class of our chapter alternating current. Today we shall discuss transformer. First of all, what is a transformer? It is a device that is used to to scale up or scale down one AC voltage, whether either to increase or to decrease the AC voltage. So accordingly there are two names. Number one, step up. Number two, step down. Step up means it increases the voltage, step down means decreases the voltage. So here are the two constructions of the transformer. Number one is, the only difference here is, let me first discuss what all these things are. This is a core, this is called core, okay. This frame is called core. It is normally made up of iron, soft iron. And this is a winding. This winding is called primary winding. The input is given from this side. This is the secondary winding and output is taken from this one. Here is the same case, but only difference here is windings are separate. Physically they are separate, but now you look, they are wound around a same core, same material. Both primary and secondary coil are around one material. Okay, so the construction difference you can easily see. Then what is its advantage we shall discuss later on. Okay, so this is all about construction. Now come to the operation, how it operates, how the voltage is increased or decreased. So it's working. How it works? Suppose we are giving AC voltage from this side. Okay. Now if you give AC voltage from this side, the current will pass through it. Of course, since AC is a sinusoidal voltage and hence the current, if current changes here sinusoidally, the magnetic field arising because of this coil, it will be like this. It will go like this, okay, and that magnetic field will link this secondary coil. Now the question is whether that magnetic field is changing or not. Of course changing, because this is sinusoidal current. If this is sinusoidal current, the magnetic field linking to this coil will be changing. That means there will be one EMF induced in secondary coil. Very simple principle, Faraday's law. So what will be the EMF induced in the secondary coil? That is of course Vs. Vs is the EMF induced in the secondary coil. But what will be its amount? Its amount will be d phi by dt. Okay. Now d phi is the flux linking to secondary coil. But the question is, we don't know what is the number of turns here. Let us suppose the number of turns on this side is Np and the number of turns on the secondary side is Ns. Since flux linking to one loop is phi, then if there are Ns number of turns, then total flux will be Ns. Now according to Faraday's law, this is nothing but Vs is equal to minus Ns d phi by dt. Very simple. So this is equation number 1. Now the question is, if EMF is induced here, now that will, if EMF is induced here, then because of that EMF there will be one current in the secondary coil. That current will be in what direction? It will be in opposite direction. To what? By Lenge's law, the current direction will be such that it will try to counter the very cause, that is the primary coil, which is producing it. So of course we do know that term is back EMF. Back EMF. What is that back EMF? That is nothing but the reaction of a coil when some outside flux is inducing some voltage in it. Here is the same case. some outside flux is going there and inducing some voltage there, and that voltage will backfire. That's why if it backfires, because of that backfire, another flux will be linking to this coil because of current in secondary. Let me come again. We apply Vp here, current flows through it. Because of that current, voltage is induced here. What will be the direction of that voltage? It will be such that the magnetic field produced by this coil will again oppose this current, or not. That means another EMF will be generated in this coil because of the back EMF in the secondary coil. So what will be that back EMF? Of course it will be equal to Vp. So Vp will be equal to, so what is the number of turns of the primary? That is Np d phi by dt. Why phi here? Because this is the flux because of which voltage is induced in the secondary. Okay. Now this is equation number 2. If you divide these two equations, Vs by Vp, this is equal to d phi by dt by cancels out, so it will be Ns by Np. Okay. Normally it is written as Vp by Vs. It will be easier to remember. So Np by Ns. Np by Ns. Now look, Vp by Vs is equal to Np by Ns implies V is proportional to N. More the number of turns, more is the voltage. That means the side having more number of turns will have higher voltage. Suppose for example, if you apply here, if you apply Vp 10 volt, then what will be the value of Vs? Provided Np is 100 and Ns is 200. This is equal to 1 by 2. So Vs will be equal to 20 volts. That means you are giving 10 volt, you are getting 20 volt. This time the voltage is increasing. That's why it will be step up transformer. Okay. In that manner, if you decrease the number of turns in the secondary from the primary, you will get step down transformer. Very simple. So next consider the current. Okay. Now see, suppose we consider that all the energies are utilized in the secondary that is provided by the primary. Whatever energy is produced by the primary, it consumes all the energies in inducing the voltage on the other side. If there is no energy loss, that means power at the input is equal to power at the output. Of course there is loss, but for example, okay. So power at input is equal to power at output. Power formula is voltage into current. Voltage at the input is Vp. Let the current at the input be Ip. Voltage at output is Vs. Let the current be Is. Implies Vp by Vs is equal to Is by Ip. This is equal to Np by Ns. Because Vp by Vs is equal to Np by Ns. Now this is the final equation of your transformer. So we do know this proportion already, but what about this? You see, more the turns, less will be the current, because this is reverse. Is by Ip is equal to Np by Ns. Very simple. The side having more number of turns will have less amount of current. Okay, this is all about working of transformer. Now let us consider the losses present in transformer. What are the different types of losses we encounter in transformer? So number one loss is flux losses in transformer. Number one is our flux leakage. Flux leakage. Now see, we are applying current at a voltage at the input. Flux is linking the secondary, but do all the fluxes link to the secondary coil? No, of course. Some fluxes are going in this manner also. That means not always all the fluxes are coming to the secondary coil. That means this is one sort of loss. Okay. You can also write it in your own language. Okay, nothing mathematically here, only definition. So if you apply a voltage here, not all the magnetic fields link to the secondary coil. Okay, that's why this is one type of, that means there is a leak of fluxes. Leak of fluxes, they are going in other directions. So number 2 is resistance of, this resistance is not loss but power loss by resistance. Okay, let me, resistance of coil. That means power consumed by the coil. You see, coil is nothing but a wire wound around the core. Wire is a conductor, definitely, but it is not a superconductor, because every material, every conductor is having some amount of resistance, and that resistance consumes some power. That power is a loss. Okay. So then number 3, eddy current loss. Eddy current loss. What is eddy current loss? Now see, current is passing through the coil. That coil is around a core material, that is iron, and iron is a ferromagnetic material. Now you see, if you ferromagnetic or it is a conductor, very simple, it is very good conductor. Now if current is passing through it and it is an AC current, that current can produce eddy current in the core material, and because of that eddy current in the core material, some power will be lost, because eddy current produces heat. From where that heat comes out? That heat is produced because of the current circulating inside the material. That means this is one sort of loss. Some energy is consumed in the form of heat. So this is eddy current loss. Number 4. Number 4 is hysteresis loss. Hysteresis loss. To understand it, let us okay, at the end I will tell you how to eradicate or eliminate or to some extent reduce all sort of losses. Okay, let me first explain all the losses first. So we have already explained these 3. Now last one is hysteresis loss. What is hysteresis loss? Recall that if you apply current to a solenoid or a material like this, the magnet inside the material inside the solenoid gets magnetized. Its magnetization is a process that comes like this, in this loop, and the current goes like this. It never comes, the magnetic process goes like this, but it never comes back in this process, in this line. It goes like this and this. It always fluctuates in this loop. Now this is retentivity, this is coercivity. I am not going in detail. That means recall that if you apply some current, the core material magnetizes. Then if you decrease the current, it demagnetizes, but still it retains some value. That is called retentivity. To neutralize that retentivity, we apply some extra amount of current in the opposite direction. That means that extra amount of current is utilized for neutralizing the magnetic effect of the material. That means this is one sort of loss, because we are using our current to neutralize that effect. This is called hysteresis loss. That means the wider is the loop, more is the loss. More will be the value of retentivity and coercivity, more will be the loss. Very simple thing. So it repeatedly, since here our current is always going plus minus, because this is sinusoidal current, plus minus. That's why the material will be at one time its north pole will be in this direction, south pole in this direction, again after another cycle it will be like this, again like this. That means it continuously magnetizes, demagnetizes, again magnetizes in opposite direction, again demagnetizes, then comes in opposite direction. It continues. In this process the loss happens. This is called hysteresis loss. Now what are the remedies of these losses? First of all, flux leakage. How to reduce the flux leakage? Now you see this configuration and this configuration. In this case there is maximum loss, okay, only a part of the fluxes are linking to the secondary. But here you look, if they are wound like this, then flux produced by primary will be almost utilized by the secondary. Of course there will be losses, but the loss in this case will be less in comparison to this one. Now come to resistance of the coil. Coil means or coil material, that is wire. This wire has some resistance and it consumes power. Now the question is how to reduce it. We cannot make it zero, but we can reduce it to some extent. How? We can use thick wires, because thick wire is having resistance. Resistance formula is rho L by A. Thick means its cross section is more. If area of cross section is more, resistance will be less. Very simple. So less the resistance, less will be the power consumption. Now eddy current. Eddy current loss was, eddy current is established in the core material. How to tackle this situation? The core material will produce eddy current. It is obviously conductor, but how to, if you laminate it, then the eddy current produced inside the material will be less, because of the lamination most of the magnetic fields will not be able to penetrate through the material, so that eddy current will be produced. We can reduce it to some extent, but we cannot completely eradicate it, because to completely eradicate it you have to completely remove the core material, which is not possible. So you can only laminate it so that some part of magnetic field will not be able to penetrate through the material. So by lamination we can reduce this, by lamination, and lamination is done by some specific materials. The last one is hysteresis. How to reduce the hysteresis loss? Of course, in hysteresis process the material is solely responsible for that. That means we should choose a material which has low retentivity and of course low coercivity. So that means, in other words, we should choose a material whose hysteresis loop is not very wide, it is narrow. Okay. So this is all about our transformer, and with this chapter is also over. Okay, thank you.